Okay, what if we have a strong electrolyte as our solute? This is going to affect the freezing point and the boiling point more because you have more particles. If you have sodium chloride, if you have 1 mole of sodium chloride, when you dissolve that, you get 1 mole of sodium ions and 1 mole of chloride ions. So you get 2 moles of particles from 1 mole of the solute. And some ionic compounds break into even more particles. So we need a factor to compensate for this, and it's called the Vant Hoff factor. It's given the symbol I, which is not to be confused with any imaginary numbers. It's the ratio of moles of particles to moles of formula units dissolved. So for sodium chloride here, we would expect it to be 2 moles of particles per 1 mole of formula units. The actual Vant Hoff factors are not the same as expected, because that would just be too easy, right? The reason is that some of the ions effectively pair up in solution and so kind of act like a single particle. Here's an illustration of ion pairing. So this sodium ion and this chloride ion are both hydrated, they're dissolved, but they can effectively pair up. They're like hanging out together, and so they go around like one particle. It's the number of particles, not what the particles are, that causes the change in the boiling point, freezing point. So actual Vant Hoff factors would have to be given to you. This table is showing for several different compounds the expected factor and the measured factor. The measured factor is always less than the expected. It's never higher. Here we've got FeCl3. So when that dissolves, 1 unit of FeCl3 is going to form 1 iron ion and 3 chloride ions. So that's 4 moles of particles from 1 mole of formula units. So we would expect this factor to be 4/1. When it's actually measured, it's 3.4 because of ion pairing. Thankfully, the correction with the Vant Hoff factor is very simple. It's just a factor, you multiply by it. So the equations are the same. You just multiply by the factor if you've got a strong electrolyte. So calculate the freezing point of an aqueous 0.1 mole iron 3 chloride solution using a Vant Hoff factor of 3.2. So here they're telling us what factor to use. So this is a strong electrolyte, and so we can't calculate the freezing point, but we calculate the change in the freezing point. And that's going to be the Vant Hoff factor times the molality times the freezing point depression constant for water. So here we are given the Vant Hoff factor of 3.2. We're given the concentration, molality, and then we have to look up the freezing point depression constant. And the units work out. .5952 degrees Celsius. And we got 2 sig figs here. So what's the freezing point? Negative 0.5952 or negative 0.60 if we round it correctly. Any questions? The Vant Hoff factor could be given to you. If it wasn't given to you, if they just said to do this and they didn't give you a factor and you had no way of looking it up, then you should use the expected factor. Okay. Strong electrolytes also have a bigger effect on vapor pressure lowering, again, because more particles. So you have to account for the dissociation of the solute when you're calculating your mole fraction. So a solution contains 0.115 moles of water and an unknown number of moles of sodium chloride. The vapor pressure of the solution is 30 degrees at 25.7 torr. The vapor pressure of pure water at 30 is 31.8 torr. Calculate the number of moles of sodium chloride in the solution. So this is a problem that's like backwards of what we were doing before. Before they'd say, okay, here are the moles or masses or something, calculate the vapor pressure. Here they're saying, here's the vapor pressure, how much stuff is in here? We're not given a Vant Hoff factor, but we do have to account for the fact that sodium chloride separates into ions. So we have to watch out for that. So we've got 115 moles of water. And we don't know how many moles of sodium chloride. The actual vapor pressure is 25.7 torr. The vapor pressure of pure water is 31.8 torr. Can we calculate the mole fraction of water? Sure we can. H2O is our solvent. The pressure, the vapor pressure of this solution, we don't have a volatile solute. The vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. We know this one. We know that one. We can calculate the mole fraction of water. So the mole fraction of water is going to equal the actual vapor pressure divided by the vapor pressure, of pure water. So the actual vapor pressure, 25.7 torr. For pure water, it's 31.8 torr. The torrs cancel out. .80817. Well, we're trying to get moles of sodium chloride, right? We got the mole fraction of water. What is the mole fraction of water equal to? How is that defined? Moles of water over the total number of moles, right? So that's going to be moles of water. And is it moles of sodium chloride or is it moles of particles? It's going to be moles of ions, because sodium chloride separates into ions. If this was a non-electrolyte, then it would just be moles of whatever it is. But the sodium chloride breaks apart. So I'm just going to call this moles of ions. Well, I know the mole fraction. I know the moles of water. So I can solve for moles of ions. It's not necessarily pretty, but we can do it. So if I cross multiply, mole fraction times mole H2O plus mole of ions. That is equal to moles of H2O. I took this equation and I cross-multiplied to get this. Then I have to distribute this across that thing. I don't know what all the math words are. So the mole fraction of water times the moles of water plus the mole fraction of water times the moles of ions will equal moles of water. Then I can put moles of water on one side I'm just debating whether I wanted to stick the numbers in now. I don't know. I started this way, we'll just finish. I'm going to go up because I'm not going to have enough room. So I'm going to subtract the chi times moles of H2O from each side. So I've got the mole fraction of water times the moles of ions is equal to moles of water minus chi H2O times moles of water divided, okay, so that was it. And then I'm going to divide both sides by chi H2O so that this goes away. Now, you can also take this equation and plug the numbers in and then solve for moles of ions. I did that in yesterday's lecture, so if you want to see that, you could check out that video. So, now I'm going to plug my numbers in. I'm going to change to a different color because it's getting a little confusing. So the moles of ions is equal to moles of H2O, 0.115, minus the mole fraction, 0.80817, times the moles, and that whole thing divided by the mole fraction. Probably 3 seconds. 0.027296 moles. That's moles of ions, moles of particles. I want moles of sodium chloride. 0.027296 moles of ions. I want moles of sodium chloride, moles of ions. If I don't have access to the actual Vant Hoff factor, I'm just going to look at the chemical formula and say, well, how many ions does that break into? 2. 1 mole of sodium chloride would give me 2 moles of ions if I ignore ion pairing. .0136 moles of sodium chloride. Any questions?
What did you subtract from the other side before you started going down?
Okay, what did I subtract from the other side? Here I've got a moles of H2O term and a moles of H2O term. So I took this term and subtracted from both sides, and that's how I got moles of H2O minus this guy right here. So osmotic pressure is really important in medical settings. Here are some photographs, well, I think they're electron micrographs, but of blood cells. So normal red blood cells kind of have a donut appearance. If you put them in a solution, say of that's too salty, osmosis will draw water from the solution, from the blood cells into the solution, causing the blood cells to shrivel up. It doesn't look like that would be good for you. It's called crenation. If you put the blood cells in pure water or something where the salt content is too low, then that causes water to flow into the cells, and it causes them to swell, and eventually they will burst. Also not good. So this is hypoosmotic or hypertonic. It's a greater osmotic pressure. No, I got them mixed up. Hyper and hypo. Man, hyperosmotic is too much. So too concentrated pulls the liquid out. Hypoosmotic is the concentration is too low. What you want is isoosmotic. Just the same. And so there's still water moving back and forth through the semi-permeable membranes, but the rate at which it goes is equal in both directions, and so your blood cells don't swell or shrink. It's a train, probably. So it's really important for IV fluids. Isotonic saline is 0.9 grams of sodium chloride per 100 milliliters of solution. That's a mass to volume sort of unit. It would be 0.9% mass to volume. And those are pretty common units in medicine. Typically you want to know the mass of, say, a medication that's being given, but the easiest way to measure how much of that solution is given is by volume, either measuring it in a syringe or a dose in a cup, or how many IV fluid bags. And so they use that unit a lot.